So I will show a little bit of studies that are going on mainly here in Turku, which we have done recently. And then, as Mio said already, I want to show some open source analysis tools because we are having 2 EU projects where we develop some quite simple Python-based analysis tools, which might be of use for some of you. Okay, but first of all, multi-spacecraft observations. Why is this useful, and what are we still tackling, and what can we actually only tackle when we have several spacecraft available? So one, of course, is that we want to know where and how our particles, the solar energetic particles, were accelerated. And at least 2 main acceleration regions are there. We know there are solar flares, magnetic reconnection regions within which particles can be accelerated to high energies as well. And then, of course, big eruptions have coronal mass ejections that drive shock fronts, and that's another potential region where they come from. And usually, when you measure the particles, you're not there close to the sun, even now with missions getting closer. Usually, you're quite far away. And then, first of all, it's quite hard to say which of these regions and the different mechanisms accelerated your particles that you measure. So what you want is actually to place lots of different little spacecraft all around, which are situated in different regimes. Maybe some are seeing the one component, the others the other component, and you would see differences. But then the next thing is also transport. Again, if you are measuring the particles far out, and especially when we talk about high energy particles, they are really accelerated mainly close to the sun, where usually our spacecraft don't reach. And so you have to deal with transport effects, which can actually modify the SEP event, the SEP parameters, and how the events look like, and the characteristics quite a bit. And especially also understanding these transport effects is also still a challenging thing for us, especially talking about cross-field transport. So for example, here you can see these 2 simulations have a similar injection width of the particles at the sun, but you can have narrow events, or you can have what we call widespread events. And there are transport effects, which we call cross-field transport or perpendicular transport, which actually lead to the particles spreading around the sun even more. So these things you basically can't tackle if you just have one observer. So you need more spacecraft in different regimes. And then, of course, you can have structures in the interplanetary medium, for example, flux ropes of pre-event CMEs or other transient structures, and they also affect how the events look like when you would observe them and if you would observe them. And there's actually a nice study I would like to refer you from Laura Rodriguez Garcia, who studied an event where we had such a flux rope in the medium, and we had observations of an event inside and outside that flux rope, and we could compare these. Okay, so the new fleet, what are we actually talking about? Of course, we have Solar Orbiter, we have Parker Solar Probe, we have near-Earth spacecraft like SOHO, ACE, WIND. Then there's still Stereo A around. And these are the main missions, of course, dedicated to measuring and to studying solar energetic particle events. But there are also a lot of planetary missions which are coming to help nowadays. So we have Bepi-Colombo, which is still on its cruise to Mercury. We have MAVEN at Mars, and nowadays we even have JUICE out there on its way to Jupiter. And all these carry energetic particle instrumentation, which can help quite a lot because they are providing extra viewpoints. And I just want to touch upon one recent multi-spacecraft case study we did with this new fleet. Here we had 6 different observer locations which observed one event. You can see the constellation of the spacecraft here. Parker was the only spacecraft behind the sun as seen from Earth. This is L1 here. And then we had lots of spacecraft, Stereo A, Solar Orbiter, and Bepi-Colombo on this side of the sun. And the eruption actually happened here on the backside. And then also Mars, MAVEN at Mars, and we saw the event all around. So you see the energetic particle increase here quite nicely. And then what was even more puzzling is that all these inner heliospheric spacecraft observed a shock crossing. So these red lines here in the plots mark when the in situ shock crossed the spacecraft. And you can also see the particles peaking when the shock crosses. So this is what we call an energetic storm particle event. And usually the scenario is so you have an event at the sun, you get immediately particles from the sun, and then you have a CME driving a shock. It keeps accelerating the particles, and when it comes towards your spacecraft and crosses it, you still see especially the low energetic particles peaking because the shock still keeps accelerating these. Excuse me. And in this event, we were quite puzzled by having this shock all around, while we knew that the main eruption was going back to the backside towards Parker Solar Probe. So we investigated this using euphoria simulations, and we tested two scenarios. And one scenario, which is shown here as scenario 2, does actually include a circumsolar shockwave. So a 360-degree shock, which we managed to simulate with euphoria, although it's actually not made to put in shockwaves. But the assumption was that this very strong eruption, which probably was even made up of two CMEs erupting close in time, produced this super wide shock, which actually even crossed the observers on the Earth side. And there's also a paper by Nicholas Wason about actually more the theory of such a circumsolar shock and how you would simulate that in euphoria. And we put the shadings here in these multi-spacecraft observations at each observer to check if the timing matches when we actually see the shock crossing, and it matched exceptionally well. So we were really surprised. Without even any tweaking of the model, it matched the observation super well. But we tried another scenario as well, because there were several pre-event CMEs in the medium. And here you can actually see this guy is a pre-event CME. And we tested if this one actually would have crossed these Earth-sided observers at the right time. With a bit more of tweaking of the euphoria simulation, it also fitted in time roughly well. But the interesting thing here is if this is really another CME-driven shock that causes the energetic storm particle event at the Earth-sided spacecraft, then it must have re-accelerated the particles of the main eruption. Because when this CME was launched at the sun a day before, no SCP event was there, nothing. So this is also an interesting scenario that you have a main eruption which can potentially feed another shock or another CME, which is already there. So in the end, we can't decide which scenario was responsible, but both actually seem quite exciting, and it's actually so nice to have so many observers around, which you can actually test with the simulations if it fits or not. By the way, this 13th of March 23 event was also very exciting in terms of the Parker Solar Probe observations, and there are two very nice papers by Emmanuel Gebarash studying in detail these observations. The one actually showed that we had electron acceleration at the shock up to 6 MeV, and that's super exceptional and very, very rare observation, and actually showing that shocks do play a big role for electrons and do accelerate them also quite efficiently. It was, by the way, also one of the fastest shocks we ever observed in situ. And then another study, Emmanuel found that in the radio spectrograms, you can actually see features that are synchrotron radiation by the shock, by the electrons. And he even found another event and reported this in the second paper. So I'd like to refer you to these to check it out as well. This I don't want to show. Here's a statistical analysis we did. One of our students here in Turku, Faber, plotted electron peak intensities as a function of proton peak intensities, which you can see here in these plots. And we separated these into different regions. So we have this well-connected sector here in green, and then we have these far separated sectors as eastern and western, which you can see here. And we had these 5 different observers. So this work is based on a catalog we put together in the Serpentine project. I'm going to tell about this a little later. But what we found is that actually the peak intensities of the electrons and protons correlate quite well. So we actually see that they seem to be accelerated in a similar way, so with a similar efficiency in these events. And we concluded that for the eastern and western sector, because they are so far away from the well connection to the flare, that here most likely it's a shock that accelerated these particles. But then in the well-connected sector, we had also this group of nicely correlated points, but then there's also this group of points which stand out, and these are electron rich, so we have higher electron to proton ratios here. And that's actually what you expect from flare acceleration, that they are electron rich. So we think that in the well-connected sector, where you actually have a chance to be connected to the flare, we see a mixture in this big sample of events. We see some which are dominated by the flare and some which are most likely due to shock acceleration. Another thing you can do with multiple spacecraft is to probe the longitudinal distribution of particles. And in the past, with the stereo mission, we have done that. We have attempted to do that. So with Earth together, we had 3 viewpoints. And then usually what people did is they described this as with Gaussian functions, which is of course very limited because the Gaussian has 3 free parameters. And if you have 3 data points, then, well, you can just start to draw conclusions. And this, of course, we don't know if the distribution is really Gaussian-like. So people have also suggested that it can look much different. And then also thing is that usually people have used peak intensities. And here's an example where you can see the 3 spacecraft and the peak intensities marked, and you see they don't necessarily happen at the same time. So when you put this together and you analyze this distribution, you're analyzing a distribution which was probably never there at any time in space. And now we try to continue this this kind of analysis. So one of my students, Jacqueline Lang, she's studying one event observed with 4 spacecraft happening in October 2021. You can see the proton time series, and here see Gaussian fits. And what she does now is she fits the distributions at each timestamp. It is quite challenging because you have to deal with lots of different instrumentation. You have to deal with intercalibration factors. Then you have radial scaling now, which was a bit more easy when we just used the stereo and Earth observations. But what we find so far, and this is preliminary results, is that the Gaussian parameters, which you can actually then plot as a function of time, show that the center of the Gaussian, so the peak of the Gaussian, actually moves away from the well-connected line slightly. And also the width of the Gaussian gets broader and broader and broader. And one explanation for this center moving away could actually be that you have a shock moving radially outwards and consecutively connecting to more and more westward field lines. But as I said, it's preliminary results, so we will also test if transport effects like drifts or diffusion effects can account for this, and we are also looking at electrons and comparing this. But this is ongoing stuff. One last thing, and here I actually want to focus mainly on just solar orbiter, after having discussed what has been done in the past. So this is about energy spectra of electrons. And electron spectra are really nice because in the end you can nicely compare them with the hard X-ray spectra of the flare, assuming that the flare was containing the same particle distribution. So it would be caused by the same electron distribution. And in the past, many statistical analyses have been done, for example, with Win3dP, and we have also done some with stereo SCPT. And what we usually find are broken power laws. So you have a break at a certain energy, and this is what we found also with the 2 different instruments. But the instruments are different, and the breaks we found are actually not at the same energy range, which is probably due to the instrumental capabilities. And we had proposed in 2021 that it could be that the real spectrum could actually look like this, that you have 2 breaks, which are produced by different effects. And it's believed that this lower energy break, around 60 keV, is a consequence of Langmuir wave generation. So when the electrons as a beam propagate through the plasma, they generate Langmuir waves, and that's in the end what actually also causes the radio bursts. And then on the other hand, this high energy break, we have proposed that this could be due to pitch angle scattering of the electrons, which is also an energy dependent effect. So now with solar orbiter, you can see how much different this looks when you have so many data points. So the spectral, the energy resolution is just awesome. And I think it's a game changer if you compare that to what we had before. And indeed, we found spectra which have this shape, which have this kind of triple polar shape with 2 breakpoints. And one of my students, Anna Maria Fedeli, has performed a statistical analysis of the 50 most intense solar orbiter electron events. And we use this COSI-CAT catalog, which Alexander Warmuth was talking about in another webinar a few months ago. And what we find is actually quite a lot of different spectral shapes. It's not always the same. We actually have single power laws, at least when we just look at the range of STEP and EPT sensors. We have simple broken power law events like before. Then we have these triple power laws. And then we also found, and that's actually the most abundant group, events which have a spectral hardening after the first break, so forming quite a plateau. And I think all this is quite exciting because it really pushes the limits of understanding these transport effects that shape the energy spectra and change the energy spectra. And this is very, very important. As I said, we probably want to compare these spectra with the hard X-ray spectra. And we actually need to understand which part of the spectrum you can actually compare and which part of the spectrum has been altered by transport effects. Okay, so much about science. Now I want to talk about the tools and advertise a bit. So there are basically 2 EU projects which we have been leading here in Turku. One is the Serpentine project. Serpentine has ended already in 2024. We had 6 partners, which you can see here in the top. And Serpentine, of course, had as big out motivation also to make use of the new spacecraft fleet. And the focus was on solar energetic particle events mainly. And now the solar project started last year. It's still ongoing. Here we have 5 partners, which you can see in the top. And solar is similar, but the science focus is more towards remote sensing observations and the solar eruption effects. But again, solar energetic particles are part of the story. And we here in Turku, we are focusing on the analysis of the solar energetic particles. And we are developing these analysis tools I want to talk about. Before I come to that, I also wanted to mention this catalog, which was the base for this one statistical analysis I showed. So this is the Solar Cycle 25 multi-spacecraft catalog of the Serpentine project, which you can find with this link, for example. And when you go there, you will also find other catalogs. So we have also a CME catalog, we have in situ shock catalogs. So there might be quite a lot of interesting things. In this catalog, we also wrote a paper about it, how things were determined. We are providing energetic particle characteristics for 5 different observer positions. And it's a multi-spacecraft catalog. So the requirement is that at least 2 spacecraft observed an event here in this higher energy proton range, 25 to 40 MeV. If we have that, it's in the catalog. And then we also provide the parameters for the 100 keV and 1 MeV electrons. And we have a lot of parameters like onset times, peak intensities, associated flares, associated radio bursts, the solar wind speed of the spacecraft at the time of the event, and the locations of everybody, and so on. So it's a quite comprehensive catalog. And furthermore than that, it's the tools. So probably the most well-known tool of the Serpentine project is the Solar Mach tool, because it has a nice web page, and you can just click there and get this constellation plot and a table telling you where your spacecraft are. But we distribute our tools at this Solar Serpentine Jupiter hub. If I have time, I will go there and show you a little bit how it looks. And there, for example, you will also find a notebook of Solar Mach. So all these tools which we have there come in this Jupiter notebook form, so that they have these cells which you can compile, and they come with a bit of introduction, explanation. So they should be self-explanatory. And for example, in this Solar Mach notebook, you get examples how you manipulate the plot a bit. For example, put some shadings, or you can make these kind of movies and stuff like that. And yeah, let's actually go there. right now and have a look. So if you want, if you don't manage to save the link, you can always Google solar or serpentine projects. You will find it here, and then there's a tab that's called Hub. And then you can click here, open the server. And that's actually here also the address of this server. And then something like this will open. So I focus here, so you will get a folder structure. And then you have serpentine and solar as folders. So for example, if we go in here, we click notebooks, and then here's the Solar Mach notebook, and here's the SAP Analysis Tools notebook. And the notebooks are these IPyNB files, so these Python notebook files. And for example, if you then click on these, it will open here in a tab. And for example, there is one which is quite powerful, but that's meant for people who know a bit how to use Python. And that one has examples of how to load various energetic particle data and sometimes also some other data sets. And it comes always also with the plotting examples. So for example, there's a lot of solar orbiter examples. And if you click here, this example, so you see you to put in a date, an averaging or resampling and stuff like that. And then basically you just have to run these cells and don't even change them. And then you get a plot like this, for example. Or for example, when you go click here stereo, it shows you what are the different data sets you can load. So there's even Mach data included and so on. And at least a minimal working example of how to plot the data is there. There are lots of tools. You can see these here in the Serpentine notebooks, but I want to show you also the solar ones, which we have just recently published. And when you go here, you will also find a folder which is called Masters Course 2025. So we have a course connected to the project, which is ongoing right now. That's also why I want to warn you, if you try to log in now for the first time to the hub and it's not working, it could be because we have a lot of people potentially using it right now. So please then try again later, or drop us a note. Anytime when you find anything weird or if something is not working, tell us, please. This would be really, really useful. But here, if you go to SCP Tools, then you find some folders, but again, you need to just check for these IPyNB files. And for example, this multi-instrument plot I wanted to show you, it opens here. When you compile the first cell, you get this nice checkbox and drop-down menu. So you can choose your spacecraft, solar orbiter, and then it opens up. Also, here are the sensors you can use and select. You can select the energy channels. You can select Mach data, lots of solar wind plasma data. You can even have light curves from sticks and so on. And then when you plot it, now this is the near Earth example, but you get very nice plots like this, which are probably already useful for publication and to analyze some events. Just quickly, there is also a tool which allows you to do pitch angle distributions and first order anisotropies, also including a background subtraction routine. So this is usually also quite nice because you have to load in the different viewing directions. You have to know the pitch angles or use the right data. So it's a nice tool for people who are not using that every day. And then we have tools doing some onset determination using a regression method. That's we have several tools which determine SCP onset times, and this is one of our newest ones. So this one just looks for breaks in the time profile of the intensities, and then you have to, of course, identify which of the break is the onset time, and you get them here with the uncertainties. As I said, they all come with instructions. You can see that here. Usually, it should be possible to understand them. But let me go back in because of time. So I'm just flashing here again the Serpentine tools. These are kind of plots you can get out. And then solar tools. There's much more than what I managed to talk about, especially for solar. There will be also lots of tools not about SCP analysis, but also about EUV waves, sticks data, so X-ray data analysis, and lots of things. So it's very useful to check this out. So here, just put again the links I didn't mention, but all of our tools are also available at GitHub. They also come with nice introduction how to install this locally. The idea with the Jupyter Hub is that you don't have to install anything, but if you want, you can, and it shouldn't be that difficult. And then you can, of course, go ahead and modify the code as you need it. And yeah, with that, I will just leave it to read for everybody. Thanks a lot.